This is a screencast for section 8.4, example 7, infinite discontinuity at an endpoint. Okay, so we have a function here, the antiderivative from 1 to 2 of dx over x minus 2. So you can see there's going to be a vertical asymptote in infinite discontinuity at x equals 2. So we're going to take the limit as c approaches, this time, 2 from the left, from 1 to c. Now we're picking from the left because 1 is to the left of c, so we want those values coming in from 1 approaching 2. So now that will find us the antiderivative, or the area under the curve, with this infinite discontinuity at an endpoint. So the antiderivative is the natural log of the absolute value of x minus 2. Fundamental theorem of calculus part 2, plug in c, subtract, plug in 1. And then I get negative infinity, because the natural log of values that are smaller than 2, subtract 2, so these values are going to get really, really tiny. That's going to go to negative infinity. And then minus, the natural log of 1 is 0. So that's going to be negative infinity, which doesn't conclude anything except for the fact that this integral diverges and has no value. So it does not converge. We cannot find the area under this curve. The now try problem number 29 says A, state why the integral is improper, then B, evaluate the integral, or state that it diverges, assuming it doesn't converge. Alright, so the antiderivative from 0 to 1 of x times the natural log of x dx. Well, in thinking about that function, the reason why it would be improper is because there is an infinite discontinuity at that lower limit of integration, x equals 0, because the natural log of 0 is an infinite discontinuity. So let's evaluate that. We're going to take the limit as b approaches 0 from the right. So we're looking for values between 0 and 1. So if we're going to approach 0, we're going to come in from the right on the number line. So the antiderivative of from b to 1, the limit of that as b approaches 0 from the right of our function. Well, let's see, x times the natural log of x dx. How do I integrate that? I don't see u substitution here because natural log of x would be related to 1 over x. Plus, that's not a composition function. I see a product of two functions. I'm going to try integration by parts. So I'm going to call u natural log of x and then dv x dx. So derivative of u is 1 over x and then v is 1/2 x squared. So if I make those, if I do my integration by parts, I have u times v, but remember, this is being evaluated from b to 1, so I need to put that symbol around. That antiderivative of this doesn't need to get taken, so I have to symbolize that as if it's already been taken, and I have to evaluate it from b to 1. Then minus the antiderivative again from b to 1, but this has an antiderivative of v times du. Alright, so now the antiderivative of v times du, well, if I'm going to take the antiderivative, I can evaluate this whole thing then from b to 1, put that on the outside. So the antiderivative of, that would be 1/2 x, is going to be 1/4 x squared. A little fundamental theorem of calculus part 2, plug in 1, subtract, plugging in b. Now in this next step, first of all, the first part of this limit is just a constant. So I'm going to evaluate that, and that's just negative 1/4. I don't need to take the limit of that anymore, so I can put that out in front of my new expression. Well, in this piece, I have all these b's where I'm taking the limit as b approaches 0 from the right. So I do need to work with this a little bit. So I'm going to subtract, and I have a 1/2 that I can take out. So I did that outside of the limit as a coefficient, a multiplier. And the limit as b approaches 0 from the right of. Now inside I'd have b squared natural log of b minus b, 1/2 b squared. So I instead factored out inside the limit a b squared. So I have b squared and then times the natural log of b minus just the 1/2 left over. So if I distributed that in, it'd be the same as this expression here with the 1/2. Next, I'm thinking I have a situation where L'Hopital's rule might come into play. So I put b squared down in the denominator as b to the negative 2. And I took the derivative of both the numerator and denominator of that limit. Well, now I can bring my b to the negative 3rd up to the numerator, and I get negative 1/2 b squared And that I can take the limit as b approaches 0 from the right. That's just going to be 0. So I get that my limit is negative 1/4.